Welcome back, Rustaceans. In this video, we're diving into one of the core building blocks of the Rust language, data types. So buckle up, grab your favorite crab plushie, and let's explore the world of scalars, compounds, and the strict but loving compiler that holds it all together. In Rust, every piece of data has a type. This tells the compiler what kind of value it is and what operations you can perform on it. Rust is statically typed, meaning types are checked at compile time. Rust's data types fall into two main categories, scalar and compound. A scalar type represents a single value. Rust has four primary scalar types: integers, floating point numbers, booleans, and characters. These are the building blocks for most simple data. On the other hand, compound types group multiple values into one. The two most common compound types are tuples and arrays. They let you bundle values together in structured ways. Let's start by creating a brand new Rust project using cargo. In the terminal, I'll run cargo new data underscore types. Then we jump into the folder and open it up in VS Code. In Rust, there are two main ways to declare a variable. First, you can be explicit and tell Rust exactly what the type should be, like this. Or you can keep it simple and let Rust figure it out for you. In this case, Rust looks at the value and says, okay, that's an integer, and it picks the default type, which is i32. Both work just fine. Rust usually figures out the type on its own, but if you want to be specific, or if Rust needs a little help, you can always add the type yourself. Let's try a few examples and see how Rust figures out the type of each variable on its own. Without us specifying any types, Rust is able to recognize what each value is. It sees that 30 is a number, so it picks an integer type. 36.6 is a decimal, so it goes with a floating point type. True is clearly a boolean, and R is a character. Even hello Rust is picked up as a stream slice. All of that is decided at compile time thanks to Rust's type inference system. Alright, let's run the program and make sure everything works as expected. And there we go. We see all our values printed: the number, the floating point, the boolean, the character, and the string. No type annotations, no errors. Rust figured it all out for us. Most of the time, Rust is great at guessing the type based on the value you give it, but sometimes the compiler just doesn't have enough information, especially when a value could be more than one possible type. A classic example is when you parse a string into a number, like this. Here, we're converting the string 42 into a number using .parse. The problem is that parse can return a bunch of different number types: i32, u32, f64, and so on. So Rust says, hey, I need you to be specific. That's why we add u32 to tell Rust exactly what we want. An integer is a number without any fractional part, just whole numbers, positive or negative. In Rust, you can use signed or unsigned integers in a variety of sizes. For example, in the previous example, we used u32, which stands for an unsigned 32-bit integer. In Rust, unsigned types start with a u and signed types start with an I. The number that follows, like 8, 16, 32, or 64, tells us how many bits of memory the number uses. So I16 means a signed 16-bit integer, and U64 is an unsigned 64-bit integer. Each of these types takes up a set amount of space in memory. Signed integers can be both positive and negative. Unsigned integers can only be positive, so they can store bigger numbers on the high end. But what happens if we try to store a value that's too big? Let's say we have a U8, which can store numbers from 0 to 255. If we try to assign it the value 256, we get integer overflow. Let's run it. And just like that, Rust catches the overflow and panics. This is because Rust automatically checks for integer overflow and stops the program when it happens. Now, you might have heard that Rust doesn't check for overflow in release builds, and that used to be true by default. But in Rust 1.73 and newer, overflow checks are now enabled in release mode too, unless you configure it otherwise. You can control this behavior in your cargo toml using the profile release section, but a word of warning here, disabling overflow checks can be dangerous. If you're not 100% sure of what you're doing, silent overflow can lead to really hard to find bugs. A famous example from game dev is the nuclear Gandhi bug in Civilization. A peaceful leader's aggression rating dropped too low, wrapped around, and suddenly Gandhi went full nuclear. That's exactly the kind of thing silent overflow can cause. Rust also supports floating numbers. These are numbers that have decimal points. There are two built-in types, F32, which is 32 bits, and F64, which is 64 bits. Both types are signed, meaning they can be either positive or negative. The default is F64 because it's more precise and, on most modern CPUs, just as fast as F32. In this example, the variable x is assigned the value 2.0. Since we didn't add a type, Rust automatically treats it as an F64, which is the default. If we want a 32-bit float instead, we can be explicit. Both are floating point numbers, just with different levels of precision. Let's run it and see the output. Everything works as expected. Rust handles both float types just fine. We'll usually stick with F64 unless memory or performance is really tight. Rust supports the basic mathematical operations you'd expect for all the number types: addition, subtraction, multiplication, division, and remainder. Let's start with addition. First, we add two integers, 5 plus 10. Rust sees both values as whole numbers, so the result of this addition will be an I32. Now let's try adding two floating point numbers, like 5.5 plus 2.5. Since both values have decimal points and we didn't specify a type, Rust uses the default type for floats, which is F64. So the result here is also an F64. What if we mix them, for example, adding an integer and a float? 5 plus 2.5? Rust won't let us do that directly, because it doesn't automatically convert between types. To make it work, we need to cast the integer. Now, both sides are F64, and the result will also be an F64. Let's run the code and check the output. And yep, everything works just as expected. Now on to subtraction. When we subtract two integers, like 20 minus 7, Rust treats them as I32, just like with addition. If we subtract two floats, such as 10.5 minus 3.2, the result is an F64 by default. And for the mixed case, Rust won't allow that directly, so we cast the integer using 20 as F64, and now both values are floats. The result is an F64. Multiplication works the same way. Integer times integer, still an integer. Float times float, a float. Mixed types, again, we cast because Rust won't automatically mix types. Division is where the type of your values really matters. When you divide two integers like 7 and 2, Rust performs integer division, which means it truncates the result. That means it just cuts off the decimal part. It doesn't round. So 7 divided by 2 doesn't give you 3.5, it gives you 3, the whole number part only. But when you divide two floating point numbers, like 7.0 divided by 2.0, Rust uses floating point division and you get the full expected result, 3.5. This is why types matter. The same numbers 7 and 2 give very different results depending on their type. Now, what if you try to divide a mix, like an integer and a float? Rust doesn't allow that directly. You'll get a type mismatch error. So you have to cast the integer to a float manually. Finally, let's talk about the remainder operator, written as %. Rust supports remainder operator for both integers and floating point numbers. If you write 43 remainder operator 5, the result is 3. That's a remainder after dividing 43 by 5, just like in basic math. Rust also lets you use remainder operator with floating point numbers. But what if you try to mix types, like an I32 and an F64? Rust won't allow that directly. It's strict about types, so you need to cast one of the values so both sides match. All right, let's run the app and make sure everything works. And yep, no errors. All the math checks out. Rust handled each operation exactly as expected, as long as we are clear about the types. Okay, so in this video, we covered integers and floating point numbers. And we also talked about how Rust's compiler can automatically detect types using type inference. We looked at Overflow, how Rust handles it in different build modes, and we walked through all the basic numeric operations, including how types affect the results. In the next video, we'll wrap up the remaining scalar types and take a look at the most common compound types like tuples and arrays. This entire series is created by just one person. If you found this helpful, please consider subscribing to the channel and hitting that like button. It really helps support the project and keeps the videos coming. Thanks so much for watching.